Okay, part two, what we're going to do is take kind of the same information we know, but we're going to put it in a different kind of format. So what the first thing we're going to look at is potential energy, which you've probably looked at before in other grades, but gravitational potential energy is found by mgh, where the m is mass in kilograms, g is 9.8 meters per second squared, and h is height, distance. So I just want to quickly think about this from the standpoint of work done by gravity, because when we did work done by gravity, we took the weight of an object, mass times 9.8, and we multiplied by the distance. It went up or down, and this is work done by energy, or work done by gravity. And the other way to talk about that is the potential energy, gravitational potential energy. So what we're really doing here is we're talking about the work done by gravity, and that is not the eraser. Okay, so we're looking at the work done by gravity here. Okay, and just make a note of that. This is the work done by gravity. Another way to talk about this is gravitational potential energy, where m is mass in kilograms. All right, so we could say, what is the potential energy of an 80 kilogram person standing 1,000 meters above ground level? Well, we'd say, well, 80 kilograms times 9.8 times 1,000 meters. And we could also, if we were looking at this from before, say, well, what is the work required to get a person up to 1,000 meters high? And we'd say, well, we'd take its f sub g, the person's f sub g, times the distance that we're going up, and we would find the potential energy. So just kind of keep that in mind. There is other potential energy. We looked at a bow problem in the chapter where the arrow was pulled back. This would be the potential energy elastic. This is where a spring would come in handy, or would come in play, either compressed or stretched. A bow, like a bow and arrow, stretched. K is a spring constant, and that's going to depend on how stiff the spring is, how hard it is to pull it back or compress it. And X is going to be the distance stretched, so whatever it starts at, and then the difference between that and what it gets stretched to. So if we were to look at the elastic potential energy in this, we would say the elastic potential energy is 1/2 the K value times 0.15 squared. And that would also give us joules. So these are all energies, these are all joules, and they're all done by doing some work on something or having it do work on something else, its surroundings. Okay, we need to talk a little bit about conservative versus non-conservative forces. Conservative forces are going to be gravity. This is not going to depend on the path taken from one position to another, and it does no work on an object moving on a closed path. Now, this probably doesn't make a lot of sense, and I don't have time in the video to explain it fully, but I'll give you an example. If I throw a ball up in the air, it's going to come back down, and we know that the work that gravity does upward is going to be negative work, and as the ball comes down, gravity is going to do positive work. So together, this negative work that's done and then positive work that's being done by gravity together will cancel each other out, so no net work is being done. That's why gravity is a conservative force. There are some other conservative forces, the spring force that we talked about in the last slide, when I compress or stretch a spring. Again, if you think about if I stretch a spring out, I do work on it, it springs back, and so again, no net work is going to be done on that closed path. Some non-conservative forces are friction, applied force, or tension, and all because they depend on the path and they do work on a closed path. So if I talk about friction this way and then I pull the object back this way, friction is going to oppose the motion this way, friction is going to oppose the motion this way. I'm going to have a total amount of work here. Work will be done this way, work will be done this way. They're both negative work, and so I will have a total net work there. It will not be zero. So you can look that up more on Google or Khan Academy and that kind of thing, or ask me, but that's the basic idea here. Conservative and non-conservative forces. All right, so if we look at that, I want to derive one other formula very quickly. I'm going to take net work and we're going to set it equal. So this is the work energy formula that we looked at before. We've done problems. if I consider the net work is done from conservative and non-conservative forces both, I'm going to set it equal to that. And that's what we did. We took work from gravity, we took work from friction, we added them all up, we set it equal, and we found some velocity changes. And we did several problems in class that way. But if we consider gravity being our conservative force and the only one we're going to consider here, I'm going to subtract this over here. And what I get is the non-conservative forces are going to equal this minus the conservative forces. Now, the conservative forces being gravity, this is going to be the change in potential energy from the initial potential energy to the final potential energy. Think about something at ground level with zero potential energy, and it has to be brought up, work against gravity, to a final height. Okay, so this is a work, gravitational work, and this is going to be the change in velocity. And you can take a minute and prove it to yourself, but basically this is what we're going to be looking at. Non-conservative forces, and friction is the only one we're going to be concerned with. There is one problem where applied force is also included here, but for the most part this is going to be friction for us. It's going to be all of the energy to the final energy minus all the energy initial. So we're going to take all the mechanical energy, that's maybe a new term, but we'll talk about it, final, plus all the gravitational energy and work, final, minus what initially we had, what it initially had potential energy-wise, gravitational potential energy-wise. So this is just another way you can use this formula that we've been using, or you can look at it from this way. It doesn't really matter. Some problems are a little bit easier to do this way. Some problems are a little bit easier to do that way. Just follow it along and make sure you're being careful where you plug stuff in. Okay, so I'm not gonna plug in the numbers because I don't have my notes with me, but let's say we're riding along a motorcycle 33.3 meters per second, and we're coasting up a hill, 8-degree hill here. Distance of 130 meters. Total height of 18 meters. How much energy is dissipated during the coasting? Okay, so what they're really asking for here is how much work is done by friction. Now, I know you wish they probably would just say that, but how much work is done by friction here? That's what they're asking. Okay, so we can do this a couple of different ways. We can take it from what we just looked at, and that's going to be work done by non-conservative forces. I probably like this one a little bit better because it kind of isolates exactly what we're looking for. We're looking for the work or the energy dissipated, lost by friction during the coasting process. Okay, so they're going to start here, they're going to coast upward here. Okay, now we can do this from the other standpoint too. We could take gravitational and frictional, right? We could take this and talk about it in terms of total work. Okay, it's okay to do it in that way, but since I just introduced this formula, we'll take a look at it this way. All right, so the final gravitational potential energy, let's say it's actually at the very top, because I believe that the problem just said we were going to do it at the very top. So it's 18 meters high. Okay, so we're going to have MGH. Okay. I'm trying to erase this and it's just not erasing. Oh, there. Okay, never mind. All right, so gravitational wise, what do we have? Final energy that this thing has. Well, it has stopped, so it has no kinetic energy. 1/2 mv squared final, it's got nothing. But it does have some height. And so the height is going to be the mass, 250 kilograms. I'm sorry, I cannot seem to erase that thing, that line, times the 9.8 times the height of 18 meters. So that all right there is what we finally end up with. This is our final kinetic and our final gravitational potential energy. minus, what did we start with? Well, we didn't start with any height, but we did, the motorcycle was moving, and the motorcycle was moving at 33.3 meters per second. So I'm going to go 1/2 mv squared, but it didn't have any potential. It was down here. So I can take all of the final minus all of the initial, and that the difference between those two is what we lost to friction. Okay, so you can calculate. All right, we have another one here. We have an object, and it's sliding down a vertical chute, starting from rest, sliding down 10 meters to the bottom. And again, you can do this from a total energy net work equals the change in kinetic energy, 1/2 mv squared final minus 1/2 mv squared initial. That first one will work just fine. This is another way to look at that. Some frictional energy will oppose it, and that is 450 joules. So if I use the non-conservative forces as the work done by friction, and I say all of the energy final minus all of the energy initial, I should be able to find how fast that it's going at the end of at the bottom. So it's at the top, it's sliding down. It's saying that the energy is 450 joules, and the way that I do this, it's upward. However, the object is going this way and friction is going this way, so this is going to be negative work, and it goes 10 meters. So this is the friction work that's being done. Friction's this way, object's going this way, so 450 times 10. The final energy, when it reaches the bottom here, it won't have any potential because it's at the bottom. It won't have any gravitational potential, but it will have, it'll be moving along. So 1/2 mv squared plus 0, that's going to be for no gravitational at the end. So this is the final energy it will have. We don't know how fast it's moving. Now, initially, what did it have? Well, it's at rest, so the initial energy was, kinetic energy was 0, but the initial potential gravitational was 10 meters up. So we're going to take the mass times 9.8, this is mgh, times 10. So energy minus the potential energy it has, mgh. Okay, and then we'll be able to solve for v. Okay, I think I don't have time actually to talk about this one, so definitely get the notes on this one. Otherwise, if I have time, I'll put another video up there.